All right, for our second talk, we'll hear about how to bring types to graph query languages, and Wenjia will be giving the talk. Go ahead.
Thank you for the introduction. Hello, everyone. I'm Wenjia. Today, I'm going to talk about the work flexible and expressive type path pattern for GQL. It's a joint work with Matías, Tomás, Bruno, Manuel, and Domagoj. The name, So we know graph database has become an important data management technology across various domains, including biology, sociology, finance, and also journalism. And there are query languages for querying graph, like Neo4j, and GQL, and GraphQL. Also, the newly proposed GQL. So what is GQL? GQL is a new ISO standard for graph language that's being developed by the same teams that develop SQL. So just to quick explain what GQL is. So in a graph, you can have node, and a node has an identifier. It has a set of labels, and it has some properties. For instance, here we have a node account. The ID is N1, the label are just account, and the property is that its owner is arena and its block is false. So it has two properties. Then we have edges that related to nodes. It has the same structure as a node. So it has an identifier, it has a label, it has properties, and also it has a direction. And the edge could be either directed or undirected. So, for instance, here we have a graph with two edges. Below, we have a path query, which is a query over the graph. So it's kind of a regular expression. So you are saying we want to match all the nodes and store the results in X. That is connected with an edge. Store the resulting Z that has an edge, which has a label transfer. And also, the property amount is bigger than 1 million. And the edge is point to another node, such that the property is block is true, and store the result in variable y. So you just match. Then you could concatenate each of these components and get the possible results. So the result in this case is the path N2, E2, and N3. And you can have more if the graph is bigger. And in X, we store N2, which is the source node. And in Y, we store N3, which is the target node. And in Z, we store E2, which is the edge. And there are some issues in graph query languages. For example, query can fail at runtime or return empty result without prior warning. And most graph queries in large number contain large number of joins to traverse the graph, to traverse the relationship. Then if the query produces an empty result, it will cause unnecessary computations, and it will hurt the efficient query evaluation. And the GQL ISO standard defines types for data. It lacks a formal type system for validating queries. Also, the GQL ISO standard is written in a mix of prose and pseudocode, make it difficult to interpret, so it requires a formalization. Now, let's look at some example to know exactly how a query can go wrong. For instance, you could write a query like the first one, where you have an incompatible shape. So you're trying to store both a node and an edge in the same variable. And according to the ISO, this is syntactic invalid. You could have also have incompatible properties. So for instance, you could say the property is block of a node is Boolean, and also it's a string at the same time. Then if you do the path query, which is like a self-references, and a node that goes from the source and the target is the same node. So this is fine, because it's going to test the property is both a Boolean, or if it's both a Boolean and a string, then the result is going to always empty, because there's no node that satisfies these two things. Also, you can have the non-existent attributes. This query give us empty, and the problem was that this attribute was that we have a typo in the attribute. But the ISO doesn't say exactly what we should do in this case. Sometimes it says you can crash or return empty. But it definitely depends on the schema. If we have this amount in a schema, then we will have result. And the other thing could go wrong is wrong usage of attributes. For instance, a Boolean as a number, and again, the behavior expected by the specification is, it depends. It could crash or it may return empty. And also, you can have error of unbound variable. And here, for instance, you are trying to reference a variable that is not in the scope. So this will give you a stuck execution. So in summary, if you have a pass query, you can have several results. One of them is that you have a result, you return something, and it's non-empty, which is happy because it's the best cases. So the other kind of result is an empty result, which is unexpected. And this empty result could be because there are some non-relevant data or due to, for instance, type inconsistency. And the other kind of result is you will get a fatal error or you stuck. And when you evaluation. So our goal for this type system is to provide a type system. Our goal for our work is to provide a type system that under approximate queries that are going to definitely be empty. So you should give warning for program that will definitely return an empty result. And over approximate the stuck evaluation. So you may want to conservatively reject program that potentially get stuck or abort during execution. And also, we want this system to be flexible. Then it would allow us to incorporate this gradually. For instance, starting with a schema, but with no type. And gradually, we can add types into it. Then we can add type annotation to the schema and get more feedback. To achieve this goal, we introduce the flexible path pattern calculus. It's FPPC, and it's a formal model of the path pattern language of GQL. We extend with new syntax by filtering with property types. And to achieve flexibility, we draw inspiration from gradual typing. We extend both the schema and the path pattern language with imprecise type information by introducing an unknown type. And the unknown type can represent labels or properties. So an overview of the system is like this. So we start from a partial schema, which may have some unknown information in it. And it's like describe what is the type of the node and what's the type of the edge that you may find. Then you have a query. And then we have a type system that either says this is an error because this could fail at one time, or it will give you a result, which is a path types and a context. And the path type basically is the type of the path that you are going to return. And the context is the type of every variable that you are binding. And taking those two things, path types and context, we could say that we could say to the user if the query is going to be empty or not. When we say but inside this one, we say if to match with our goals, we say if there is an error, then it's an over approximation. And if we say empty, then it's under approximation. And also, we have the flexibility because we can have the partial schema. And the type system of our FPPC can detect all errors for a previous example. For example, the first example, the incompatible shapes is yield type because the meet between a node type and an edge type is not defined. Then for the second example, the incompatible properties raise an empty result because the meet between bool and string is bottom. Then non-existent attribute is ill type because the attribute could not be found in the schema. Of course, it depends on the schema. If we have this typo amount, then it's going to be well type. Then another one is the long usage attribute where raised and empty because type error in the conditional tense is propagated to the patterns. Then the final example is ill type since X is absent from the context. Then to validate the formal development of our FPPC and support interactive experiment with type graph queries, we implement a Python prototype. And this design supports informative feedback and allows the analysis of partial valid queries. For instance, consider the pattern. This query is syntactic valid. Both contain a type inconsistency or a reference to an unbound variable. And the type checker will give us the diagnostics, says there is warning message about the type inconsistency, and there is a variable cannot found error. Then we prove some properties, for example, type safety of the type system. And it guarantees that well-typed path queries cannot get stuck or produce runtime error. And another important property is empty properties. It ensures that if a query type checks, but its type is flagged as empty, then it will definitely return an empty result due to type inconsistency. And we also prove the important properties in gradual typing, gradual guarantee. And it ensures that if we're removing some type annotation, then it will not introduce either type or runtime errors. So in summary, this work makes these contributions. We present the FPPC, and it's a formal calculus for GQL, and extends with the ISO standard with property-based filtering and gradual types. And we extend the past pattern language with type property expression and allowing nodes and edges to be filtered based on both labels and property types. And we prove the empty property, type safety, and gradual guarantee. And also, we provide a prototype implementation of FPPC. And our current prototype, for the future work, because our current prototype focuses on a core fragment of GQL, so for future work, we are supposed to, we may need to support the full range of GQL queries. And we could extend features such as aggregation and negation enable predicate. And a possible solution is a set theoretic approach. Then we could explore optimization for query evaluation under this typing enhancement. Also, we can do further refinement to the interaction between schema evaluation and gradual typing in graph database. Due to the time limit, I just provide an overview of this work. You can scan the code if you want to know the full details of our work. Thank you.
You'll start first. How do you evaluate your work?
Sorry?
How do you evaluate your system, your type system?
Evaluate our type system.
Do you have case study that you run?
Because GQL is quite new, so there is no graph query database. So we haven't do this kind of case study. Yeah.
Hi. Hello, Max New, University of Michigan. So you have a runtime monitoring kind of system to run queries that have partial type information, right? So a big problem with gradual typing for higher order languages is that this can get very expensive. So is it relatively cheap for this kind of query language, or do you still run into performance issues with that?
I think because because of the performance issue of gradual typing, I think if we support like higher order function, we will also have these issues. But we can improve the performance of graph query is that you can address empty. So the focus to improve the performance is not is about we can address empty result, empty warning.
Right. But I'm saying you don't have higher order functions in
No,
this
we
setting,
don't have
right?
higher
so
order
it
functions.
might be that it turns out to be acceptable over
Yeah.
Okay.
So we don't have a higher order function. So maybe we don't need to consider the performance issue. But if we have a higher order function, I think that would be an issue.
Okay.
Yeah.
Yeah,
Thank you.